parametric function here. And we were talking about, so we found that at t equals 1, t equals 1 corresponded to this point right here. And just, let's see here. So it's awfully quiet out there. Can you all hear me?
Yep.
Okay, good. Just want to make sure. So this was t equals 1. And we know the parametric functions, what's the independent quantity in a parametric function? What's the independent quantity?
T.
T. And what's the dependent quantity?
The coordinate xy.
Both coordinates, right? This is the whole point of parametric functions. So all the stuff we're doing is for naught if you don't have that basic understanding that parametric functions are about the independent thing or entity is this value of t. And then the dependent thing is an ordered pair, xy. And then when you get into Calc 3, you'll be working in R3, which is like three-dimensional space. And it'll be the same thing. Independent variable will be t, and then the dependent variable will be an ordered triple, or a location in 3D space. Okay? And so let's talk about, let's just review a little bit here. So let's talk about derivatives here. So dx dt, dy dt, and dx dy. So we got dx dt, and dx dt was 3t squared minus 6t, and dy dt was minus 8t cubed plus 6t minus 1, and dy dx was dy dt divided by dx dt, so it'd be negative 8t cubed plus 6t minus 1 over 3t squared minus 6t. And so we could get those exact values by plugging in the value of t, 1, but without doing that, let's predict dx dt, and so we said that the direction of the curve was this way. So dx dt then would be positive or negative here at t equals 1.
Negative.
Okay.
Positive.
Okay, I got one negative and one positive. How about the rest of you? How about one more? Let's cast the deciding vote. Is dx dt positive, negative, or zero-ish here at t equals 1?
Negative. Negative.
Okay, so negative is right, because for increasing t, for a small change in t, x, we generate points to the right, or in the negative x direction, right? Going through here like this. And because of that, dx dt is less than 0. What about dy dt? For increasing t, what does y do?
Also negative.
It's decreasing, so y values are decreasing on those points as t increases, so also negative. So what about dy dx? Looking at the graph.
Now it's positive.
Positive, so that has nothing to do with the direction of the curve anymore, right? Dy dx strictly has to do with, as it's like the slope in our xy coordinate system, right? Or as x increases, so that would be going this way, regardless of the fact that t is taking us this way. As x increases, y increases also, according to the inclination right there of the curve. And so dy dx we expect to be positive. And then we talked about, all right, what about the second derivative? With respect to x. And what is this? This is about if you let x change a little bit, how does the derivative change? So you can think about derivatives for x values less and derivatives for x values greater. And as x increases, what are those derivatives doing? What's that rate of change doing? Is it increasing or decreasing? So this is our situation like this, right? Rate of change. So each one of those lines is like is representing a rate of change. And so as x increases this way, those rates are decreasing, getting less positive. So we expect the second derivative with respect to x to be
Negative.
negative. And we're going to find that exact value right now. So we're going to find the exact value. This is the second derivative. And so when we take the derivative of this, we're really taking, this derivative dy dx is in terms of t. So we take that derivative in terms of t. So that won't be d dy dx dx. It'll be d dy dx dt. And we know that's the quotient rule. So the quotient rule is low d high, so 3t squared minus 6t. D high is negative 24t squared plus 6 minus high d low, which is negative 8t cubed plus 6t minus 1 times the derivative of the bottom is 6t. Please check my work. Please speak up if I make a mistake. Speak up right away. 6t minus 6 all over low squared. Nope. Low is what? 3t squared minus 6t squared. All right, does this look like I've followed the quotient rule correctly? Low d high minus high d low over low. I think I got it. Anyone see a mistake?
I also have this.
Same thing?
Yeah.
Okay. So let's try to simplify this as fast as we can without making a mistake. So, wow. Okay, so to the fourth. So it looks like negative 72t to the fourth plus 48. Is that 34? 24? 24 minus 24t cubed. So minus 72 plus 24 is not, no, plus 48.
It's negative 48, isn't it?
Yeah, so this is positive 48, and this is negative 72. So I think that makes negative 24. Is that right?
Yep.
Okay, we'll go with it. All right, so, and then t, oh man, this isn't worth it. Let's just, we're plugging in t equals 1. So simplifying this top is just not worth it. We'll just leave it expanded like that, because all we're gonna do is plug in t equals 1, and that will make our life a lot easier. I think it's not worth it to try to simplify that top. But like I said before, this is not this, right? It's not the second derivative with respect to x. It's the second derivative with respect to t. So how do I get then the second derivative with respect to x?
Divide by dx dt.
Yeah, so I'm going to do the same thing I did with the first derivative when I took dy dt and I divided by dx dt. Now I'm taking d derivative dt, so I need to divide that by dx dt. So we're going to take that and divide by dx dt. And then we'll have the second derivative with respect to x. Okay, so here we go. So plugging in 1, we got 4 terms here. Plugging in 1, this looks like negative 3. Please check my...
Professor?
Yeah.
Should that be squared on the bottom?
No, it shouldn't. It should not. Thank you. Thank you very much. Minus 3. That looks like times minus 18. Check my work. I'm plugging 1 into these. This looks like, that's 5. And this looks like minus 3 to me. And this looks like 0. And that will be over minus 3 squared. And that whole thing over minus 3. All right, how did I do plugging in positive 1? Minus 3, minus 18, that's 5, -3, and 0, -3 squared, I think I got it. But please speak up if you see an error. And so here we go, and we're expecting negative, right? We're expecting this to turn out negative. And so that is 54 over 9 all over -3. And I think that is that -2? And so that is less than 0, like we said. The rate is decreasing, right? The rate of change is decreasing as x increases. So the second derivative with respect to x is negative. Okay, so any questions on that? So in your homework problem, after you find this derivative, they recommend that you multiply by t over t because of what these functions look like. You wouldn't do that here, but I just want to talk about that. When you multiply by t over t, it greatly simplifies your numerator and denominator. But what I want to tell you is, so dy dx stays the same when you do that. But now your numerator with multiplied by t is no longer dy dt. And your denominator multiplied by t is no longer dx dt. So you're preserving the value of the whole ratio, or you're preserving dy dx by doing this, but now your numerator and denominator are no longer dy dt and dx dt. So just keep that in mind. So like here, we could have combined these and made this -3 cubed. But if you do this step, you can't do that because you just made the denominator is no longer dx dt. Okay, so that's it for rate of change and derivatives. We're going to move on to one last topic here. Any questions? Okay, very good. So let's move on to let's see if I can find this fast. I meant to have this open. Oh. Gee whiz. There we go. That'll work fine. Okay, so let's talk about remember signed area. Signed area. And let's that was a particular what? This was a particular accumulation function that we looked at, right? So we at the beginning of the course we looked at this idea of what you know how fast a quantity is changing at every moment. You want to know how much of it you have at any moment, and that quantity could be anything. We talked about volume and arc length and surface area and signed area and population and any temperature and any quantity. And so we could apply this our findings about you know how fast the quantity is changing. You want to know how much of it you have. So signed area was one example, right? Was the one example of an accumulating quantity, and we applied our accumulation function to that. And so if we wanted to write the signed area as a function of x, or any accumulation function for that matter, I want to write an accumulation, in this case accumulation of signed area. What was the key to that? What was that function? What's the structure and form of that function? We know that we want to write the accumulation of signed area as a function of x. What does that look like? And if most of you don't know this, we have failed you miserably. This was one of the biggest themes of the course.
Surface area?
No signed area. So signed area.
Do you take the integral from a to x, or 0 to x, and then the rate of change is that height?
Good. Very good. And the rate of change, do I put x in there?
No, you could do t or n or
something else, right? So we need something else. So now, looking ahead, that our parametric functions are in terms of t. I don't want to use t here. I want to use u, but that we used to use t for that. So this is the idea, right? If you wanted the accumulation of a quantity, you do the integral from a to x of the rate of change du, the rate of change times du. And what does that represent right there? Rate times a little change in x represents what?
the derivative.
No, not a derivative.
A small change in signed area.
Good, right? It's a small amount. It's a little bit of signed area. Or d signed area, right? And then the integral means summing up, starting from a, accumulating those little bits of signed area, each bit calculated by rate times change in x, right? Rate times change in x. Accumulating up all those bits starting from a all the way up to x. Okay? And what was the rate of change of signed area? So we said all that we need to write a signed area accumulation function, all we would need is the rate of change of signed area. Who remembers what the rate of change of signed area was?
The function itself.
Yeah, so if this is f, what's the rate of change? The rate of change is, for a little change in x, how much does the area change? Well, it changes by the height of that edge right there. That's where we're adding on area. We're adding on area at the right side of this, say, green region. And so how much area do we add on? We add on the amount of that edge. Right now we're adding a lot on. Now we're adding less on because that edge is shrinking. Now we're adding even less on. So the rate of change would be f of u du. Because that's the rate of change of signed area, the value of the function. Okay, and another way to say that is that's just y, right? That's just y, and this is dx. It's just we need another symbol to represent every x starting from a, accumulating to x. So that's kind of a little bit of a review there, and let me back it up here. So right here, at this value of x, say 1, what can you tell me about the value of the signed area right here at x equals 1? If a is negative 3. So we're going to start at a equals negative 3. So what about surface area, signed area at 1? What can you tell me?
The accumulation of all signed areas would be at x equals 1 starting from negative 3 would be less than 0.
Okay, he's saying that the accumulation of signed area starting from negative 3 up to x equals 1, he says is less than 0. Negative. What about the rest of you? Agree with that?
I agree.
Yeah, I agree.
Exactly, right? Because signed area takes into account that when the function is negative, it actually is the signed area is decreasing. It's a negative contribution of the gray area. So by the time you get to 1, the amount of negative accumulation has not been satisfied by the green positive accumulation yet. So the signed area would still be negative at 1. And what about at 0? What could you say about the value of the signed area at 0?
At 0, the signed area is at its lowest value.
Good. Okay, so it's its lowest value because it's going to start increasing now. What else could you say about that value? How would the value of the signed area relate to the actual area of the gray region?
They would be equal.
So the signed area would be equal to the value of
The
the
absolute value.
Okay, so I don't want to put an absolute value on it. I just want to say, how does the value of the signed area at x equals 0 compare to, or how does it relate to, the actual area of the gray region?
They're the same.
Is it the same? Not the
The
same.
signed area is negative, and the actual area is always positive.
There you go. Right. So if you took so that signed area at 0 would be some negative number, right? It would be some negative value, and it'd be someone said it would be the lowest value that the signed area hits. That's right. So it's the lowest, the biggest negative, and it would be opposite of the area, right? So it would be that negative value. If you took the positive version of it, someone said absolute value. That's the right idea. Take the opposite of that signed area, you'd get it'd be the area of the gray region. Okay, so now what about in any questions? That's all a review of signed area. But the rate of change of signed area is the value of the function. It's the height of that leading edge where the area is being added on. Okay, so what about in parametric functions? So here's the deal in parametric functions. We are going to maintain this exact same approach in parametric functions. We're going to be thinking about x increasing from left to right. And we're going to accumulate starting from some x value to another x value. And so we're going to take the y value as the rate of change. So we're going to base it all on this. But what we're going to do is just going to rewrite this whole function in terms of t. So that's the only difference. So it's completely the same approach as what we did before, but we're going to rewrite this function in terms of t. And then we're going to see that because the curves in parametric function are different and weird, and they're not, y is not a function of x, we're going to see some kind of cool and strange things happen. But we're just keeping in mind that our approach is exactly like this. Okay, exactly like that. But we just need to rewrite this function in terms of t. Fair enough? Okay, here we go. So, what is our parametric function? So this parametric function, say, is, I'm going to call, instead of using f and g, because I'm using f for the y value, let's say that our parametric function is x equals, say, p of t, and y equals q of t. Is it fair? So there's my parametric function. X is a function of t, and y is a function of t, and these given values of t generate ordered pairs that we graph in the normal xy plane. Okay, so if we want to write the surface area as a function of t, first of all, our limits of integration will still be from a to x, but we want so we want the t values, the t value corresponding to a, so I'll call it t sub a, right? This is the t value that gives you a value of x equals a. All right, and then to x, so then I'll call this to t for the current value of x. So that's pretty simple, right? So to rewrite the limits, we just want the t value corresponding to the starting value of x, a, and the t value corresponding to the the current value of x. All right, next, f of u. So what is f of u in our parametric function? So what is f of u? Well, it's the y value. So how will we replace f of u in our integral here for accumulating signed area in parametric function as a parametric function? What will I put here instead of f of u?
Q of u?
All right. You said q of u. What do we think? Exactly, right? Because q of u is y. Again, we definitely don't want to use t, right? So t is going to be reserved for that's our independent variable. We need a new symbol that means every t, starting from the starting t to the current value of t. All right, very good. And so then, what about du? How am I going to rewrite du? And so actually, let's use a different. So since u was every value of x from a to x, let's just pick a new symbol here instead, so that we know that u is an x value, and then this new symbol will be a t value, just to be absolutely clear. So let's use v. Okay? So v is a t value. It's every value of t starting at the starting to the ending value of t. Okay, so now we need to rewrite du, which is essentially dx. So what is that in our parametric function? How do I rewrite dx?
Would that be dpv?
Okay, kind of.
The rate times dv.
Okay, so let's start in terms of t here. So yeah, good. Both of you are very good. Okay, so here we want to, given x is a function p of t, what is it that generates a small change in x? What has to change first to generate a small change in x?
Would it be dv dt?
Okay, so yeah, so we need dt, right? So given a small change in t, that will result in a small change in x. And what is this? How do we get the small change in x? It's a theme we've had all semester long. Given a small change in your independent, the change in the dependent is what?
That small change in the independent times the rate of change.
Times the rate of change, right? Good. So the rate of change is what gives us small changes in our dependent variable, given a small change in the independent. So what's my rate of change?
P of t?
Just p of t? Is that the rate?
P prime?
P prime of t. Or db, or if you wanted to say, you could say dp dt if you wanted. So yeah, so or dp dt. But let's call it p prime. So this is a huge theme we've had all semester. Given a small change in your independent variable, in this case t, your change in your dependent, x, will be the rate times the change in t. So now, what will I write for du? What will I write for du here? So this is like y, and du is like dx. So what will I write?
P prime
dp dt?
P prime of what?
P
V
dv.
dv. So that's like my dx, right? That's like my dx, the rate of change of p times dt, but we need a new symbol for t. So these v's are every t from ta to tx. All right, so we got it. So again, this is totally the same approach that we did before. It's just we're rewriting our function times y times dx in terms of t, which will be our function for y, times dx, which will be the rate times dt. Questions on the derivation?
Yeah, I have a question.
Please.
So would that signed area would that give us the signed area for like x versus t or x or y versus x?
No, it's still going to be y versus x. It's still going to be signed area in the xy plane. It's just the vehicle for generating it is just now t instead of x. So back here, the independent variable of this whole thing was x. The only difference now is that the independent variable is t. All the geometry is the same. It's still x increasing, and we're generating a signed area using the height or the y value. Does that answer
Okay,
it?
I see. Thank you.
Yeah, sure. Okay, so let's do it for this, and I want to start right here at the intercept, and that's t equals, forgot what it equals. This is x. So what is t? I guess I'll have to. Anyone read? I wrote over the top of it.
-1.
Negative 1.608. Okay, and so then I want to say I want to generate the signed area accumulation function starting from t equals negative 1.608, and that's an a value of negative 10.991. Is it okay? So we're going to start accumulating right there from the x-intercept. And regardless of which way the curve is generated, we're going this way because the x increases this way. But to keep it simple, t is also increasing that way also, so it doesn't confuse the issue here. Make some room for us here. So can we write this? First of all, let's write the accumulation function. So our signed area would be, now with respect to t, would be the integral from what? What's our starting value?
-1.
1.608.
Yep, the t value for our starting x to t. And then what will I put in here? So q of v, what is q of v for this curve right here? What's q of v?
The y value at a certain t point.
Well, it's going to be every, right? It's going to be, we want every t value starting from negative 1.608 to t. So how do we express every y value?
GV.
What's that?
GV.
Okay, yeah, so exactly, g of v. So rather than writing that out, so in our case here, it's going to be g of v. That's right. So rather than writing that whole thing out, let's just use g of v. That's good. Right, that's the y value. And then times what?
F prime of v.
F prime of v dv. And we could write those out, right? We could write out the negative 2v to the fourth plus 3v squared minus v plus 4 times 3v squared minus 6v dv. But that's fine too. So this is our signed area function. And what will that look like? So do I have that right there? So I'm using u, and I'll just change it to v to be consistent with what we're doing. And we're starting at what, negative 1.608. So does that signed area function agree with what we just wrote? Instead of f of v, I just put in the actual derivative there, 3v squared minus 6v. So I think we got it. Okay, so now I want to know what the signed area is up to the t value at the maximum. So here we are. We're accumulating signed area. And what would be true about all these values of signed area so far? What would it be true?
They would be positive.
Positive and equal to what?
The height of the graph at, oh wait, no.
Equal to total area?
Good, right? So the signed area so far, all these values of signed area would be equal to the actual area, right? Wouldn't it? What I want to get this thing off this. Doesn't like it. There we go. Come on. All right, whatever. So let's just to this point. So this would be then, this would be the signed area of t right here, negative 0.946, which is something I was going for the max. Okay, it's the maximum value of the function. But so the signed area at negative 0.946 would be this integral from negative 1.608 to negative 0.946 of gv dot f prime v dv. And that would be positive. And let's see, so that would be, we can just have GC do that for us. That would be A of negative 0.946. So we get 32, we get a positive number, and that positive number is, in this case, is actually the same as the area because the curve is always above the x-axis in positive y territory. Making sense so far? All right, so when my x value crosses this point here where there's another x-intercept, okay, and we keep going, what is it going to find there? What's the effect of this? The fact that this curve is here. What's going to be the effect of this curve being here if I continue to let t increase?
Will it have to like find the difference between the y values?
Okay, so you're saying that it'll start coming here, and the x value will cross over this, and it'll say, oh wait, there's a curve here. I better do something different. So for this t value here, say negative 0.7 or negative 0.6, does that know anything about what's happening for lower y values with the curve and future t values?
Not yet, because those t values haven't been reached yet.
Yeah. So when we keep going here, what will this look like? As I keep going, and what will the region look like? Will it go down to this curve, or will it keep going down to the x-axis?
To the x-axis.
The x-axis.
Yeah, it's gonna know nothing about this. This won't influence it at all. These are future t values. It could care less. All it cares about, this function and this animation, all it cares about is what's the value of y, and I'm going to take that all the way down to the x-axis. So as we keep going, It was really smooth last night. It was nice and fast and smooth. So it's just going to keep accumulating signed area, in this case area, and it doesn't care about this curve at all. So this is t equals 0. What happened? Oh no, I thought that was t equals 0. I guess it's t equals 1. Okay, so here we are at x equals 1 or t equals 0. And so this would be, this would be the accumulation of signed area for my final t value of 0, which is at x equals 1. It's like it's the very tip of the nose of this, like aardvark or whatever this thing is, anteater. So that area that I'm showing now is 52.02, and that's for t equals 0 or x equals 1 at the tip there. So now if we continue to let t increase, what's going to happen? As t increases, our y value is going to now start tracing along this curve. And tell me about dx. So for increasing t, what are my values of dx?
Negative.
Dx is negative. So what's going to happen to the signed area as I keep increasing? T.
It's going to become negative.
The signed area is going to be negative?
It's just going to decrease.
It's going to start decreasing.
Right.
Yeah, that's probably what you meant. It's going to decrease by now the amount of this gray area underneath the curve for the current value. So now as t increases, x is decreasing, so my dx's are negative, and just like signed area, sometimes it decreases, right? And so the signed area is going to decrease by the amount of the gray. So if I were to find the signed area at the second x-intercept, which is x equals 3.26, or bummer. Anyway, so whatever t value this is, it's going to be something greater than 1. Let's call it 1.5 or something like that. So suppose it's 1.5. What will the signed area at 1.5 represent? The signed area at 1.5 will represent what? Right? Remember, the signed area at t equals 0 gave us all of the area of the blue and the gray. So now if t keeps going, and I'm guessing that, I say it's t is 1.5 here, what will that signed area represent?
Just the area between that's confined to the parametric function.
Yeah, right, this blue area, right? So now the signed area function will give just the value of the area of the blue function above the x-axis, like kind of inside the curve. Because when we started coming back this way, dx was negative and all this gray got subtracted out. So this will be the blue area, or the area of the aardvark's head. So because we can go backward, as t increases, x can go negative, and then you also have the signed area will be opposite when your y values are opposite. You get all these new situations, right? So what will start happening as we keep going? What contribution will this region make to the signed area now? Positive or negative?
Very large negative addition, so it subtracts a lot.
But look, x is still decreasing, and y values are negative. So therefore, signed area will increase now. Because both y is negative and dx is negative, this will have a positive contribution to the signed area. This, when I'm drawing in black. So things get crazy, right? Because these parametric curves are different. They're crazy, and so that has these kind of some weird impact on the signed area function. Okay. Any questions? I hope that made sense. I hope you liked it. I think this subject's really cool.
I just had a quick question.
Sure.
It's kind of just like a real world application for this. Like, what would we use this for? Like, how would we see this?
I can't think of something, but not everything. There's lots of things in math that are just beautiful in and of themselves, and not everything has to have a real world application. That there may be something, but
Okay.
Math has beauty in and of itself, and so we appreciate that. And yes, real world applications are incredibly important, but they're not everything with math. They're not the whole ball. They're not everything.